Okay, good afternoon to everyone. Can you see me and hear me well? Okay, thank you. Just wait another couple of minutes and then we start. Another minute and then we start. Okay, let's start. Now, good afternoon to everyone. As I mentioned last time, we're now starting our part which is dedicated to credit risk. And as I mentioned last time, within credit risk, we're going to look first at the components of the expected loss, i.e. PD and LGD. And we'll start by looking at models that actually are used to estimate the probability of default of a borrower. Now, within these models, a relevant role is played by scoring models, which, as we will see today, are models that are very much focused on past accounting data. So they use past historical accounting data mostly, sometimes also behavioral data, to estimate a score and eventually a probability of default, okay? Now these scoring models, the most common one, the most well-known ones, are discriminant analysis, and we'll spend quite some time today discussing discriminant analysis, and logit or probit models, which are more kind of regression models, and neural networks. Okay, so those are the models that we'll try to examine today. Okay. Now, just to recall, as we mentioned last time, what are the three main factors that drive the future losses on an individual credit exposure? These are the default, which of course is a binomial variable. It could either be 1 when there is a default, or 0 when it doesn't default. The exposure at default and the loss given default, which is basically 1 minus the recovery rate. And as I mentioned, today we're going to spend our time on the probability of default and on models that estimate the probability of default. So when we want to estimate the probability of default, the first key point is how we define default. And here there could be, let's say, more objective criteria, like, for example, when there is a delay in payments of capital or interest payment, or a more subjective one, like when the bank thinks that the borrower is now unable or unwilling to pay, okay? And as I mentioned, the probability of default can be estimated either using backward-looking models, like scoring models, that mostly look at past information, like financial ratios, news, and so on, or forward-looking models that are mostly models that rely on market data. For example, they rely on bond spreads or on equity market data, which could be prices or volatility, okay? Now, just to give you an idea of how scoring models work, they can be used in two alternative ways. One is you can use as input financial statements data. Think about, for example, profitability ratios, leverage, liquidity ratios, and so on. You can use information coming from Central Credit Registry that are available in some countries like in Italy, in France, and so on, where basically banks convey their information about borrowers, and therefore an individual bank can actually find data and information for more banks in these databases. And sometimes internal data, like for example, how did the borrower behave? Have there been overdrafts with respect to the credit line? And so on, okay? Now these models can be used to estimate directly a probability of default. And then based on the probability of default, this can be translated, for example, in a rating grade. Say, for example, from 1 to 10, okay? Or more frequently, this is most generally the case, the same inputs can be used to generate a score, and based on that score, then a rating grade is assigned. So say, for example, all the borrowers that have a score between 30 and 40 go to rating grade 3, okay? And then what one can do is estimate the historical default frequency associated to that rating grade, okay? And therefore, this can be used as a proxy of the PD. This is more commonly what is generally done by banks. So what they do is they use a scoring model based on the inputs that I mentioned. They estimate, based on the scoring model, a score. This score is then translated into a rating grade. And then from the rating grade, a PD is estimated. And the PD in this case is more simply the historical default rate for that rating grade, okay? So that's how most scoring models actually work, okay? Okay. Now, having said that, which is more general for every kind of scoring model, let's try now to understand how one specific credit scoring, which is very common out there, discriminant analysis, actually work, okay? So discriminant analysis works on a set of inputs that could be, say, financial statements ratios, okay? And as I mentioned, behavioral data like bank overdrafts, okay? And generally what you do is you divide the borrowers between two groups, okay? So what you could do is, for example, I take 500 companies, say, and I take their data 1 year ago, okay? And then I look at those companies that defaulted in a year and those that did not default, okay? So I divide them in two groups, the good ones and the bad ones are the ones that actually default, okay? Now, then what I do, I try to understand through discriminant analysis, and we'll see how the technicalities work, how I can best discriminate between those two groups of borrowers, okay? Clearly, the idea is that the two groups have values of those variables that are actually structurally different between the two groups, okay? So to give you an idea, assume that we get two variables. On the y-axis, we have interest expenses over turnover. And on the x-axis, we have unauthorized overdraft over total exposure. These are two variables that one would expect that a good company has, other things equal, lower values. If you're a good and sound company, typically you have a low ratio of interest expenses over turnover, and you have a lower amount of overdrafts over total exposure. Therefore, you would expect the good companies to be characterized by low values of these two variables. Okay. Now, here you have the bad companies in red that tend to have higher values of both these variables than the ones of the good companies. Okay. Now, this means that, generally speaking, the idea underlying discriminant analysis is that if you take, say, one company randomly, and you look at the values of those two variables for this company, well, if these values are corresponding to the point highlighted in this chart, the black star, then you would expect that with a very high probability, this is a good company, i.e. it belongs to the good companies group that did not default, and vice versa, it has a lower probability to belonging to the bad companies. Okay. Clearly, the idea is that you work out of samples. So basically, you use the historical sample of good and bad companies to characterize those information, and then you use those inputs to try to understand a company outside of the sample, whether it's more likely to belong to the good or the bad companies. Okay. Here, for example, we have another company that is more likely to belong to the bad companies because it has much higher values of both variables. So we could conclude that there is a very low probability that this company would belong to the good companies and vice versa. Okay. But clearly, there's also a gray area. I mean, if we take a company like the one highlighted in this chart with the black star, you can clearly understand that in this case, the model would be much less effective in telling me whether this is a bad or good company. Okay. So this is just the underlying idea of discriminant analysis. But how can we really actually compute the the scoring model, and how can we understand what are the weights that we would assign to the different variables that we want to use? Now, generally speaking, the score can be seen as a kind of weighted average of the scores that the company is getting in each one of the above mentioned variables. Or if you want, like a weighted average of the scores that the students actually reports in a number of subjects. Okay. Clearly, the weights are chosen in such a way that the good companies' scores are as far as possible from the bad companies' ones. Okay. Now, we must also say that we could also use a discriminant analysis model to estimate a probability of default, i.e. to estimate the probability of being good or bad. Okay. But more often, the scoring model of this kind is not used to estimate a PD, but simply to estimate a score, which would then use to assign a rating. Okay. So once again, we could use a scoring model to directly estimate a PD, but this is not typically done in the real world. Okay. So the problem that we have is, how do we move from the natural variables that you see here? Again, we have the same two variables. On the y-axis, you have interest expenses over turnover. On the x-axis, you have unauthorized overdrafts over total credit exposure. Okay. And you can see, for example, that the bad companies, which are identified by the red dots, have on average values of these two variables which are clearly higher than the good companies, which are here identified with the green spots, okay? So what we have to do is try to move from those natural variables to a synthetic one, which is a linear combination of the original variables, okay? So the two original variables are interest expenses over turnover and overdrafts over total exposure. Now, what you have here is a discriminant analysis score, which we call dx, where basically you see that this is a combination of the two variables, x1 and x2. And the problem we have is to decide what is the weight that we want to give to the two variables, gamma 1 and gamma 2, okay? So here is the problem that we have to deal with, okay? How do we compute those weights, the two gammas, okay? Or if you want, the vector of gammas. Now, let's look at the following steps. So we want to find a function, dx, which is basically the product of the vector of weights, the coefficients, if you want, and the variable x, which is another vector. That's why we use the transpose for the weights. Now, assume that we have x1 and x2, the two vectors with the mean values for the two variables for good and bad, okay? I mean, they could be two variables, they could be n variables, 10 variables, let's say. But x1 and x2 are the vectors of the good and bad, okay? Then we could estimate, we could compute the score d1 for the good companies using the vector x1, and the score for the bad companies using the vector x2, which would both use the same weight vector, or coefficients vector gamma. The variance, as for any linear combination of random variables, is equal to what we see here. The transpose of the vector of the coefficient times the variance covariance matrix times gamma. Now, what are the best weights? The idea underlying discriminant analysis is that we should try to maximize the difference between the two scores, i.e., we should maximize the standardized distance between the good and the bad means. The good and the bad means are also called centroids in discriminant analysis. And centroids is basically the mean value, okay? The mean values for good companies and bad companies standardized by the standard deviation, okay, of the discriminant function, which analytically is the difference between the two means that we saw here, and we have to maximize that. Now, as you can see in the next passages, now, first of all, for simplicity, we maximize the square of the above, and we get what we have here with the variance covariance matrix, which is easier, okay? Therefore, we have to maximize this value Q. And if we derive that, we can find out that the result, you can see that in the bottom line, is represented by, the result in terms of the vector of the weights, the gamma vector, which what we are interested in, is the inverse of the variance covariance matrix multiplied by the difference between the vector of the values of the variables for the good companies and the vector of the variables for the bad companies, okay? Now, if we follow that logic, the idea is that the weights that we use to compute the discriminant function are chosen in a way that in some way are maximizing the distance between the two centroids, the two mean values for the good and the bad companies. And of course, we try to gather as close as possible the values of the score for the good on one side and the bad on the other side around their respective centroids, which again, I repeat, are the mean values, okay? And if we do that, then on top of the centroids, which are the two mean values for good and bad companies, we can also compute let's say, a cutoff point, if you want a rule of thumb, which is the midpoint between the two centroids. As you can see in the equation in the bottom of the slide, is the arithmetic average of the two discriminant score functions for good and bad companies, and in some way use it as a kind of threshold, i.e. By basically saying if the value of the individual company is higher than this threshold alpha, then we classify it as a good company, and if it's lower, we classify it as a bad company. Okay. Now, to better understand what I said so far, so basically the idea is, as I mentioned, if we are above alpha, then it's a good company. If we're below alpha, then it's a bad company. Of course, by computing the discriminant function for company I, which is out of the sample. Okay. Now, to better understand what I said so far, let's try to look at a very simple example whereby we can compute these discriminant function and at the same time the cutoff point. Now, assume for simplicity that we have only 38 companies in our database. Of course, this is very far from realistic, meaning that, as I mentioned, typically banks, what they do, they have samples which are much wider and with quite a large number of defaults as well, okay? But let's say for simplicity that out of these 38 companies, 24 are good, i.e. after 1 year they're still alive, and 14 of them are bad, i.e. after 1 year they actually defaulted, okay? And again, for simplicity, we only take into account two variables, as we did before. One is an accounting variable, interest expenses over turnover, and the other one is a behavioral kind of variable, i.e. overdrafts over total exposure, okay? Now, here are the values of these two variables for the 24 good companies, which are on the left, and the 14 bad companies, which are on the right. And as you can see, in the bottom of this table, the average values for these two variables for the good companies, 29% and 11%, are much lower than the average values for the good companies, okay? Here are the values for all these companies of the two ratios represented graphically, okay? Now, what we do, we compute the two vectors of the variables for the good companies and the bad companies, okay? So these are the mean values, exactly the ones that I just mentioned, okay? And then we compute the variance-covariance matrix for each group of companies, i.e. the healthy one, the good ones, and the bad ones, okay? Now, the average sigma, the average variance-covariance matrix is here computed as a weighted average of those two variance-covariance matrices, i.e. in the case of the good companies, the weight is 23/36. In the case of the bad companies, 13/36. And that's the weighted average variance-covariance matrix. Now, first we compute the inverse of this matrix, and then we apply the Discriminant function, as we mentioned above, i.e. gamma coefficients, the gamma vector, is computed as the product of the inverse of the matrix and the vector of the good companies minus the vector of the bad companies. And what you see at the end is a discriminant score. It is a discriminant analysis function. We call it Z, and for company XI is computed as the two weights. As you can see, both of these weights are negative. And the reason being that both these variables tend to get lower variables for better companies. Therefore, the weights, the coefficients are negative, okay? Meaning that the better is the company, other things equal, and the lower is the value of these variables, okay? Now, what about computing the score for one individual variable, okay? Now, let's say that we compute the score for one company which is in the sample in this case. Now, this is actually computed, sorry, there was a mistake originally in the slides. This is company 7, not company 2 as it appears here. It's company 7. Now, if we get to company 7, we can see that company 7 has a first variable which is 27% and the second 5%. So if we apply those coefficients to 0.27 and 0.05, we get a score of minus 185, okay? So that's the value of the score for that variable, okay? And for that company. And we can do that for all companies that were in the sample. This is done, for example, here. As you can see, for company 7 is minus 1.85, but you can compute it for all these companies. And as you can see, on average, the good companies tend to have higher values for these score than bad companies, okay? And they are not perfectly separate because unfortunately there are cases when they are not actually separate. For example, you can see in the good ones, there are two companies, company 2 and 3, which have very negative values, which are close to the ones of the bad companies, okay? While the others have clearly much lower values, okay? Sorry, much higher values, okay? Much lower in absolute terms, okay? The two group values are clustered around their respective centroids, even if they are not perfectly separate, okay? Now, we can then compute the cutoff point as the midpoint between the two centroids. So we take the two centroids by applying the scoring model to the mean values of the variables of the two subsamples, and we get that the cutoff point is minus 3.97, okay? Now, in this case, we can then use that as a threshold and as a kind of this decision criteria, okay? So for example, here we computed that for company 7 and it was minus 1.85. Now the cutoff point is minus 3.97. So because minus 1.85 is higher than this cutoff point, then the conclusion should be that company 7 is a good company. And in reality, that is actually the case. Company 7 did actually belong to the group of good companies, okay? And this is actually done, can be done for all these companies, and therefore can be used to decide whether they're good or bad based on this cutoff point, okay? Now, if we do apply that rule, what do we get? We get a kind of classification rule that would lead to these results? Basically, it would tell us that if you take the true groups, so those that are really true, out of the 24 that are really true, 19 would be classified as good, okay? However, out of these 24, unfortunately, 5 would be mistakenly classified as bad, okay? So out of the 38 companies, 50% here would be classified correctly. Similarly, if we look at the true groups, we had 14 bad companies. Out of these 14, 10 would be correctly classified as bad, 26% of the total sum. But unfortunately, 4 of the bad companies would mistakenly be classified as good, okay? So if we take the correct classification rate, we have 50% plus 26%, and this is also called the hit rate, i.e. how many of the companies would be classified correctly according to our model and the threshold, the cutoff point that we chose, okay? Pay attention, I mean, if we look at our, for example, here, you can see that out in these good companies, 2 of them, 2 and 3, company 2 and company 3, using this cutoff point of 397, would be classified as bad, while they belong to the good companies, okay? Now here in this simple example, I applied the model and the rule to companies that were in the sample used to compute the scoring model, okay? Usually this is not really how it works in practice. In practice, what you do is you use a sample of companies to estimate the scoring model, and then you actually apply that to other companies for which you want to understand whether they will default in the future or not, okay? So you typically apply that out of sample, okay? Okay, let me stop 1 minute here to see if there are questions on what I said so far, whether it's all clear. Oh, sorry, there was a question. Professor, could you please explain again the dependent variable and the method for estimating the parameter? I'm not understanding why we do not use variable with dependent variable 1 with company fields or otherwise. Now, okay, so the question is, in deciding what are the weights, so what are the coefficients, why don't we use simply a kind of regression model whereby the dependent variable is either 0 or 1, i.e. whether it defaulted. If it's a default, it would be 1, and if it did not default, it would be 0. And then we use as independent variables the accounting ratios or the other variables that you want to use. But rather we use this kind of very peculiar model, which is called discriminant analysis. Now, the model that you are mentioning, i.e. using 0, 1s as dependent variables in a regression, this is actually the other model that we're going to look at in a minute, which is the logit model or the Prodit model, okay? Those are very simple regression models where, as we will see, the dependent variable is indeed taking values of either 0 or 1. And then all the accounting variables will be the independent. This is a different kind of model, which is basically grounded on the idea of finding what weights we should assign to these variables in order to best discriminate, to better differentiate between good and bad companies, okay? And if it is a different technique, which is based on this methodology that we just described, i.e. to find out what kind of linear combination of those variables best discriminates between good and bad companies. It's a different kind of idea, it's a different kind of model, but it's very common out there. For example, a very famous and well-known discriminant analysis model is the so-called Z-score that was introduced many years ago by an economist, Ed Altman, who's a close friend of mine, by the way, that published this study many years ago. And it's actually described in this equation, where the variables that he used are working capital over total assets, retained profits over total assets. So that's a profitability. There are a couple of profitability indicators. There is a value of leverage, which is based on the book value of debt and the market value of the assets, which takes into account the market cap of the company. So it's, if you want, it's based on, it's a model that can be used only for listed companies. And then it has turnover over total assets. And this is these are all variables that take higher values for better companies. Therefore, the weights are all positive, okay? Now, the Z-score, it's very well known, and there is even a, if you want, a button on the Bloomberg that is used to compute the Z-score for any kind of company, okay? So it's a very, very common one. And methodologically, is completely different from a regression model like the one that you asked me. I don't know whether I answered, okay? Another question, wouldn't it make sense to put the threshold not in the middle as it is a worse error? That's a very good question. The question is, shouldn't actually we put the cutoff point not exactly here in the middle, but rather take into account that the two error types, i.e. classifying a good company as bad and classifying a bad company as good, have very different costs. That's what we're going to focus on in a minute, okay? So whether we should change this cutoff point, this threshold, based on the cost of the errors, okay? Okay, I don't know whether I answered the question or whether there are other questions. Okay. So another point that we should highlight is a parameter which is very important, which is called the Wilks lambda. The Wilks lambda is a ratio that basically minimizes the ratio between the residual deviance after we have basically classified the companies into two groups, good and bad, and the total deviance. So basically, what you see at the numerator is first the sum of the differences between the score of every individual company I and the average value belonging to the group 1, which is the good companies, and the average score value for the good companies. So this is basically the centroid for good companies. See, this is the sum of the differences between the score value of company I and the average value for the companies belonging to the good group, squared, so that, you know, positive and negatives are not offsets. And the same applied to the sample of the bad companies, okay? So by distinguishing two, I basically separate those deviances, okay? And the idea would be that if the model is a good one, and it's able to, if you want, differentiate as good as possible the good from the bad, and at the same time make those values very close for the good companies and very close among the bad companies, then this numerator should be much lower than the denominator, where the same computation is done without distinguishing between good and bad companies, okay? So the idea is, if the model is a good one and well discriminates between good and bad, and at the same time gets values of the discriminant score which are close among good on one side and close among bad on the other side, then the numerator should be very close to zero, and especially should be very different from the denominator, much lower than the denominator. So this lambda is a ratio that is basically taking a value of 1 if the model is completely useless, i.e. it doesn't discriminate at all, and it takes values very close to 0 if the model is very effective in discriminating between good and bad companies, okay? Now, next step. As I said at the beginning, theoretically, we could use a discriminant analysis model directly to estimate a probability of default. As I mentioned, most often what is done is that a discriminant analysis model is used to get a score, and the score is then used to assign to a rating rate, okay? However, theoretically, we could do that, but i.e. compute directly a probability of default. But in order to do that, we have to first estimate so-called prior probabilities. Sorry, I forgot to mention that this can be done if we assume that the variables that I'm using are normally distributed. And this is not really so realistic, because some of these variables are actually financial ratios that are truncated between 0 and 1. Now, basically, if we have prior probabilities, and I'll mention in a minute what they are, we can compute the probability of belonging to the group 1 or the probability of belonging to group 2. So what you see in this equation, for example, here, this is the probability that company I belongs to group 1 given its values of its ratios xi, okay? i.e. it's the probability of belonging to the good companies. That one, the second one, is the probability that company I belongs to the bad companies, the group 2, given its values xi. The probability of belonging to group 2, i.e. to the bad companies, is clearly the probability of default. This can be computed, as it is shown here, using this ratio pi1 to pi2. Pi1 and pi2 are the prior probabilities, i.e. the a priori probability for a company to be good or bad, okay? Now, these prior probabilities are actually computed in different ways, but typically they can be proxied by the composition of the sample. So, for example, in the example that we saw before, the pi1, which is the probability a priori of belonging to the good companies, is given by the ratio between the number of good companies in the sample. So it would be 24 out of 38. While pi2, which is the probability of belonging to the bad companies, would be 14 out of 38, okay? So if we compute these probabilities, i.e. more specifically, if we compute the probability of default, which is the probability of belonging to group 2, using these prior probabilities, those are the values that we get. And those are estimates of the PD. Remember, for company 2 and company 3, we made a mistake with the cutoff. And similarly, we estimate PDs which are very high compared to the fact that these companies actually belong to the good companies, are good companies, okay? Clearly, as you can see, the PD for the bad companies are much higher, okay, on average. So if we have this, if we're able to estimate this probability of default, then we could construct an alternative criterion for classifying companies between good and bad. I remember we put this threshold, cutoff point here in the middle, okay? One alternative criterion could be, well, let's classify it as good or bad, depending on whether the probability of belonging to good is larger than belonging to the bad companies. So if you want, an alternative criterion is, rather than classifying as good any company whose score is larger than this cutoff point threshold, we classify it as a good company if the probability of belonging to the good company is higher than the one of belonging to the bad companies. And it can be shown in the last equation of this slide that this new cutoff point is alpha prime, and it's exactly like the same before, alpha, but you would add this component, which is the natural log of the ratio between pi2 and pi1. Because pi2 is generally lower than pi1, okay, then the cutoff point would be basically become more optimistic, okay? In our example, as the probability of belonging to the bad companies 37%, the cutoff point calculated considering the probability is lower than the previous one, and therefore relatively more optimistic, okay? So in some way, what we're doing, we are pushing the cutoff point to the left, i.e. making our model a bit more optimistic, okay? Now, a final adjustment is the one that you mentioned, i.e. not simply taking into account the probability, a priori probability, but rather also taking into account the cost of the errors. And this is a very important point. Now, the idea here is the following. If I classify a good company to the good companies, of course, I don't make any error. If I classify a good company into the bad ones, the cost is rather limited. In this example here is just the foregone interest margin. So if I have a good company and I don't lend money to this good company because I think it's a bad one, you know, I don't lose much. Simply, I would lose the interest margin that I could have made by lending money to this company. If vice versa, I classify as good a company that is actually bad, then the cost is much more significant. And it's basically the LGD, the loss given default, i.e. I'm risking much more than the foregone interest margin, okay? Therefore, because the cost of the two errors is very different, we could actually try to make our model more conservative by reflecting the cost of the two errors, okay? And clearly, this alternative criterion would allow to basically push the cutoff point to the right this time, i.e. making our model more conservative. I.e., how would it work this way? By taking into account both the, let's say, the a priori probability and the cost of the errors, okay? Now, in this case, the rule would be classifying companies based on the expected cost of the two errors. And basically, the expected cost of the two errors is a function of the two types of errors, i.e. the cost of classifying as good if it is bad, and the cost of classifying as bad if it is good, but also the probability of being bad and being good, which are the two mentioned probabilities, okay? Now, if we do that, the cutoff point gets actually moved to the right, because typically this ratio, okay, this ratio that you see here is positive, is larger than 1, sorry, and therefore the natural log is positive, and therefore the cutoff point gets moved to the right. So, for example, here you see the decision prompted by the model that we saw before based on the different cutoff points, okay? And the cutoff points here are alpha, the very simple one, without the priors and without the cost of the errors, alpha prime, which is the one only taking into account the probabilities of default, and the one that takes into account both the cost of the errors and the probabilities. As you can see, the final one is much more selective. Indeed, there is no error in terms of the second type of error, okay? There's no error here, okay? All the bad companies are correctly classified as bad, but there are quite a number of errors in terms of the classifying good companies as bad, okay? Now, the change from alpha prime to the second one makes the model more selective. We have taught our model to be more prudent. Now, keep in mind that this adjustment could be corrected, for example, if we provide more collateral. If the borrower provides more collateral, clearly the cost of this minus 70% would be significantly decreased, because the LGD would be decreased. And therefore, this would also allow to basically make the model less selective, and therefore push again the cutoff point towards the left, okay? So these are different classification rules by not taking into account probabilities and cost of errors, by taking into account only probabilities of default, and by taking into account also the cost of the errors, okay? Let me see if there are questions before I move on. No, okay. If there is a question, just write it on the chat, okay? Now, what about the selection of the variables? So far, we made the example only taking into account the two variables: interest expenses over turnover and overdrafts over the exposure. But clearly, a discriminant analysis model has typically many more variables, say 7, 8, 9, 10 variables, okay? How are these variables selected? Well, they are selected in two different ways. One is a priori. So basically what we do is we try to think about what we believe are the relevant variables, okay, a priori. We identify, for example, we could say, well, I think it's very much based on profitability, on liquidity, on leverage, and I include these variables a priori, okay? And then I'll try to understand empirically what are the weights that should be assigned to these variables. Another criterion is more, if you want, inductive, i.e., I take, let's say, 30 variables, I include them in the model step by step by including all variables and then removing the ones that have a lower discriminating power, okay? And I can do it two ways, i.e., adding up variables progressively, or include all of them at the beginning and then removing progressively. So it's two different ways, but basically the logic is very much inductive. I try to see empirically what are showing the best discriminating power, okay? To conclude with discriminant analysis, I think it is important to highlight that this model has two underlying assumptions, which are quite strong assumptions. One is that the variance-covariance matrices of the independent variables are the same for the two groups of companies, i.e. good companies and bad companies, okay? Unfortunately, the empirical data tend to suggest that there is heteroscedasticity among the two groups, i.e. that the variance-covariance matrices are not the same. Then there are sophistications within the discriminant analysis framework that try to address that, but to be frank, no one is really using them, and the problem remains. The second problem is the one that I mentioned, i.e. that if I want to use directly the discriminant analysis model to estimate a PD, I would be assuming that those variables are normally distributed, which is not really empirically the case, and therefore it would be a problem. But again, I want to stress what I mentioned already, i.e. banks typically do not use a discriminant analysis model to estimate PD directly, but rather they use them to estimate a score, then based on the score assign a rating, and then based on the rating compute probabilities of default, okay? So to sum up discriminant analysis, customers are divided in two groups, which are assumed to have different means. Subgroups are described based on past data, so that new data can be assigned to one of them. And it's very much a descriptive tool. There is no underlying structural model. I mean, it's not saying those companies are going to default because of this factor, okay? There are some underlying assumptions which actually have some implications in terms of the realism of the model. So that's very much about discriminant analysis. I just stopped 1 minute to understand whether there is any doubt or request of clarification as far as DA is concerned. Okay, so let's move to a second type of model, which is very much what was implied in a question that one of you asked earlier, i.e., can we actually have an alternative model where rather than this strange kind of algorithm, we have a simple, let's say, regression model where we estimate the coefficients based on a regression function. Now, here the point is very simple. We are still using exactly the same inputs. It's still a scoring model, okay? But rather than using a discriminant model, we use a regression model, okay? And how does a regression model work? Well, basically, what we do is assume we have an equation where the dependent variable is either 0 or 1. So again, we take, say, 500 companies in the past, and after 1 year, we see, for example, that 50 of them actually defaulted. So these 50 companies, we give to the dependent variable a value of 1. All of those which did not default have zeros, okay? So our dependent variable y can take a value of 0 or 1, depending on whether the company defaulted, okay? The independent variables are the same variables that we use in regression analysis, i.e. financial statement ratios, behavioral ratios, and so on, okay? And then very simply, based on this dependent variable that can take a value of 0, 1, or the independent variables, we estimate a regression model, okay? Therefore, this way, we estimate the coefficients beta that we assign to each one of the independent variables. And clearly, because the dependent variable can take a value between 0 and 1, we can say that the output y of this model, if we apply that to a company which is out of the sample, is a proxy of the probability of default. The closer it is to 0, the closer that company is to the good companies, and therefore the lower its probability of default. The closer it is to 1, the y variable for company I, the closer this company is to the defaulted companies, and the higher is its probability of default, okay? This is the simple underlying idea of a linear probabilistic model. Now, what is the problem with the linear probabilistic model? Now, the problem is that if we do that, and if we apply this regression analysis, it could well be that if we estimate y for a company out of sample using the beta coefficient, we could take a value for y which is below 0 or above 1. There's no reason why we shouldn't be actually getting values that are outside the 0-1 range. And this clearly represents a problem, okay? Usually we can truncate these values between 0 and 1, but clearly we have further problems. The variance of the residuals of the linear model is not constant, but suffers from heteroscedasticity. And therefore the estimate of the coefficients, it's imprecise. So typically, rather than the simple linear probabilistic model, other models are chosen outside there. The most common one are the probability and logit model. Actually, to be completely transparent, the most common one is the logit model. Okay. Now, what is the logit model? The logit model is a model whereby the output, without actually needing to truncate the values between 0 and 1, is ex ante limited between 0 and 1. So the idea is that the dependent variable 1 is the result of a function that you can see in the final equation, whereby basically the linear relationship is actually adjusted through an exponential transformation, a logistic transformation. So the independent variable wi is given by the linear function that we saw before, and combining the two, we actually obtain the logit model, okay? And in this transformation, the dependent variable y is actually constrained between 0 and 1 as we wanted it to be, okay? And I must admit that the logit model is probably, together with the discriminant analysis model, the most common model that you see out there now in banking, okay? Again, you could use the logit model to directly estimate a probability of default as the dependent variable. In reality, this is almost never done. What we do is we use the logit output to assign a rating, and then again, we use the default rate for each rating grade as the default probability estimate, okay? Probit is an alternative transformation to the logistic one, again with the codomain, which is between 0 and 1, but the model is a different kind of transformation. I don't want to go into the details of that. Finally, again, as I mentioned, the PD can be used directly or as an output for the rating, and then from the rating, we derive the default frequency, okay? Finally, just a couple of words on so-called inductive models. There is another class of models that are really very different from the ones that we've seen so far. Now, the credit scoring models that we've seen so far basically try to understand what are the fundamental relationships that explain the economic and financial health of a company. And so basically try to look at the structural features of a company and try to, if you want, choose the variables based on that. As I mentioned, we tend to think that, generally speaking, companies that have high profitability, high liquidity, low leverage, and so on, tend to be more unlikely to default. And therefore, we include those variables into the models, and these are in some way the structural features of the company, okay? Inductive models, so there is an economic logic here, okay? Inductive models are completely agnostic. And if you want, very similar to the idea that is now very fashionable and very trendy, which goes under the name of machine learning, or if you want, artificial intelligence. What is the idea behind these models? Well, you know, I don't care. I don't know what are the economic features that explain a default. I simply try to understand what are to recognize, let's say, regularities, okay? Empirical regularities, okay? So I don't know actually what explains the fact that a company defaults or not. What I do, I construct, say, hundreds of variables with the financial data of the company, with the behavioral data and so on. I put them into a black box, okay? And then I tell the machine what companies default and what company did not default. And I ask the machine, you tell me what do you think are the regularities? And I do that in a very uncritical, agnostic way, okay? So inductive models are very much black boxes that try simply to understand, identify empirical regularities, okay? And one, for example, technique is neural networks. Another one is genetic algorithms. But basically, they all share the same underlying idea. I put down all the data of the borrower, and then I ask the machine to find out what are the empirical regularities and basically find out what are the rules, Okay, and this, process that with strong computing power can even take a short time and be very efficient, and sometimes actually perform better than an economic model that has a clear underlying economic rationale. Okay. And in some way, artificial intelligence, machine learning are very much based on that. And it's the same, idea that sometimes we find, for example, in medicine. I mean, we don't know exactly what is the underlying reason of a disease. What we put down, the data for thousands and thousands of patients with different outcomes, and we ask the machine to understand what is the empirical regularity and tell us what are the relevant factors without any necessary clear economic, rational logic. Okay. Okay. So this is just to give you a general idea. Okay. Having said that, I think we can now look briefly at a few questions and exercises. But again, let me stop a few seconds to understand if there is any question or doubt. Okay, you're still seeing me and hear me well, right? Okay, thank you. Okay, let's look at a couple of questions and exercises together. The first one. A bank has analyzed the financial statements of good and bad companies, customers, and found that the ratio of equity to total asset was on average 50% for good and 20% for bad. The ratio of liquid assets to short-term liabilities was on average 2 for goods and 0.4 for bad. And the variance covariance matrix between the two ratios and its inverse are the following. The bank wants to use the information in discriminant analysis model, compute the coefficient of the discriminant function. Now, for simplicity, you have the Excel file here with all the calculation, but for simplicity, I reported the result here in this slide. Now, first of all, what are the inputs? Now, the first table reports the vector of the variables for good and bad. Remember, it says the ratio equity to total asset was 50% and 20%, good and bad. The ratio of a liquid asset to short-term liability was 2 and 0.4. And so here we have the two vectors, good and bad. So if you want the X, the variables. Here are the two variance covariance matrices, sigma and inverse of sigma. Here are the two coefficients, the two weights, the gamma function, okay, the discriminant function. These are computed following the equation that we saw before, and you see here, these in the Excel file are the two gammas. It's the product or the inverse of the variance covariance matrix and the difference between the two vectors of good and bad. Okay. So these are the two weights of the two variables. Then you can apply these two coefficients and compute the mean values for the good and the bad. And these are the centroids that are reported here. These were the two first questions, the coefficients and the centroids. The third question is the threshold to be used to separate good and bad. If the ex ante probability of having a bad customer is 10%, the narrow costs are not available. So here you can compute the cutoff point alpha as simply the mean of the two centroids. If you take the average value of these two centroids, you get the cutoff point without taking into account the priors and without taking into account the cost of the errors. Now we're saying the prior probability of being a bad company is 10%. Now, if this is the case, we can compute the cutoff point taking into account the PD. That is, remember, alpha minus the natural log of the ratio of the two probabilities. And because this ratio is lower than 1, the resulting alpha prime with the prior probability is lower. So the model becomes more optimistic, less selective. Finally, you are asked to compute the same cutoff taking into account the cost of the errors, which of course are higher for the first kind of error, i.e. classifying as good or bad company. And in this case, you have to add again the natural log of the ratio between the two types of costs. And therefore, because this ratio is larger than 1, this cutoff point gets increased and it becomes, your model becomes more selective. The threshold is pushed towards the right, okay? Okay. Second question. In a discriminant analysis model, if a borrower offers collateral that reduces the expected LGD, his/her score remains the same while his/her PD gets reduced. His/her PD remains constant while the cutoff point decreases as the cost associated to a wrong classification change. His/her score remains constant while the cutoff point increases as the cost associated to a wrong classification decreases. Score, PD, and cutoff point remain all unchanged. Now I give you 1 minute and you tell me what is the correct answer. Come on, no one wants to try? I see B. B, his/her PD remains constant. That's correct. The PD is not affected. While the cutoff point decreases as the cost associated to the wrong classification change. That is correct. If I offer a collateral, the LGD goes down, so the cost associated to a wrong classification, i.e. classifying as good or bad company, decreases, and therefore the cutoff point moves to the left, making the model more optimistic. Okay, that's correct. It's B. 3. A customer has applied for a loan of 500,000 euros, providing a cash collateral of 100,000, so that in the event of default, the loss to the bank would be equal to 80%. So here is already telling us what would be the cost of the wrong classification, i.e. the LGD, 80% of the loan. The rate applied would be 12%. The cost of funds and all other operating expenses for the bank would amount to 10%, leaving a net profit margin of 2%. So here it's also the other type of the cost associated to the other type of error, because if I decide not to lend to a good company because it's a bad one, and then it's in reality a good company, what my cost would be the foregone interest margin, which would be 2%. The customer score, based on a discriminant analysis model, is 6.1. This is below the minimum threshold for a loan to be issued, which, based on the error cost shown above and the prior bad probability of 10%, would be equal to 7. So basically here it's saying, look, the threshold, if we take into account probabilities and cost of error, is 7. This customer has a score of 6.1. And the question is, how much more cash collateral should the customer provide, leaving the 12% rate unchanged for his loan request to be approved? So here are all the inputs. The threshold is 7. the probability of being, the prior probability of being bad is 10%. The LGD, so the cost of the first type of error, is 80%. The other one is 2%. Now, first of all, you can compute what would be the threshold without priors, without costs, okay? In order to do so, you have to do the opposite, i.e. you start from prior, from 7, and you deduct the natural log of the ratio between the probabilities and the natural log of the ratio between the cost of error. This is done here in the Excel file. You start from here is 7, and you actually compute the alpha, the cutoff point, without the priors, without the error costs. And you see the equation above, which is doing exactly the same. Then what you do, you compute the cutoff point with the priors only, because those are not changing, okay? Now with the priors only, of course, the cutoff point is lower, is more optimistic, okay? And then what you do, you actually look at what should be the cost of lending if bad. So that first type of error that here has a cost of 80%, if we want the threshold to be equal to the score of our company, which is 6.1, and here this is done here, is actually the cost of lending should be 32%. Therefore, if you want it to be 32% and it's actually 80% now, you have to decrease it by 47%, i.e. you have to add an amount of extra collateral, which is 47% of actually the exposure, okay? And that's 237,372. The total exposure was 500,000 euro, okay? So it's basically it's a reverse process where you try to understand first what should be the cost of lending for the threshold to be 6.1, and therefore you adjust the cost of lending, which was the cost of lending to a bad borrower was 80%, you have to decrease it by 47%, and this allows you to estimate what is the extra collateral you need. Finally, it is asking you to compute the customer PD, and here you just apply the formula that we saw before, and it actually is equal to 5.8%, okay? Question 4, consider the following statements on linear probability models and logic models. Linear probability models need to be truncated between 0 and 1 for their results to be equal to those of the logic model. Results to be equal. Linear probability models need to be truncated between 0 and 1 for their output ranges to be equal to those of a logic model. Linear probability models and logic models have the same coefficients, but the estimated PDs are different because logic models involve a nonlinear filter. Linear probability models, unlike logics, generate biased estimates. Now, I leave you 1 minute. Which do you think are correct of these 4 statements? Who wants to try? See? Anyone else? Indeed, C is the correct answer because this is correct. The first one is not correct because the results are not the same, just as the third one is not correct. They are not having the same coefficients. So the 2 and the 4 are correct, therefore the correct answer is C. Finally, now we have 2. The scoring model has been modified by adding a new input, which is 95% correlated with an input that already was in the model and that was considered highly significant by the bank's experts. Which of the following changes in the model's performance would you expect? A strong improvement in the model since the new input will also be highly significant. A strong decrease in performance because we have duplicating information. This cannot be told in advance as it depends on the specific data sample. Almost no change in performance. What do you think is the correct answer? If you want the most likely answer. Let's see. Okay, sorry, there is a question. So the correct answer here is D, almost no change in performance. Because basically, if it's 95% correlated, clearly, it doesn't really change a lot. So there was a question saying why statement 3 in the previous question is incorrect. Let's look. Linear probability models and logic models have the same coefficients. This is why it's incorrect. They don't have the same coefficients. One is a linear model, the other one is a logic transformation, so they don't have the same coefficients. Okay, that's the reason why this statement is incorrect. Okay. Finally, last question. Assume a bank is evaluating using the same historical data alternative scoring models to estimate the PDs for a set of bonds. Which of the following statement is correct? While logit and probit models have the same coefficients, the resulting PDs are different. Linear probability models output need to be truncated between 0 and 1 for the results to be equal to those of the logit model. Linear probability models, unlike logit models, produce unbiased result. While logit and well, this is very similar to. No, it's the same. Sorry. Yes, it's the same. Sorry. So forget about this question. Okay. Any question? Any residual question on what we saw today? Okay, so I'll see you next. Sorry, there is another question, but Professor, don't we estimate the linear models and then simply apply the nonlinear transformation? No, we do the linear transformation first and then we estimate the coefficients, okay? So it's a different technique. Okay, so I'll speak to you next Friday.